We'll proceed in new topic that we have initiated, vector and commercial calculus. Vector and commercial calculus. This will take us to the artificial and machine learning kind of scenario. So post this, probably we'll start Bayesian theorem in machine learning. Vector and commercial calculus. This is what we are pursuing. Now we are talking about a force field or vector field. Force field or a vector field. If I have a force field, then what is the work done? This is what typically we are talking about. Now consider that there is an item that would move from here to here. There is an item that would move from here to here. It can move like that. The item is fixed here and it cannot move anywhere. It will move along the line only. Okay. The example what I am giving is, consider there is a bolt. Okay. There is a bolt that is kind of, you can rotate in a nut. There is a nut and bolt. So there is a bolt that is kept here and it will go inside this one. If that is the case, then consider there is a force field. This is force field. Under this force field, now this bolt starts moving like this and it goes from point A comma B to another point alpha comma beta under this force. What is the work done by this force when it is moving a bolt from this point to this point? If that is the case, then it is force vector dot displacement vector. This is displacement vector. Okay, this is very nice when force vector is numerical vector, like 2i plus j, 4i plus 5j, I plus 16j. This, if the force vector is numerical vector, then force vector dot displacement vector is the work done. Okay, if force vector is not a numerical vector, if it is an algebraic vector, xi plus yj minus yi plus xj, minus yi plus xj divided by x square plus y square. This is force field. If this is the force field, then force into displacement is the work done. Okay, anything, anyway. My idea is whatever we see, we bring it into consideration of energy, because energy cannot be destroyed. So energy calculation leads to the better and refined calculation. So in that way, if there is a force field is coming from one energy source. There is one energy source kept. Because of that, there is a force field. This energy source can be magnetic field, electromagnetic energy source, can be a magnet, electromagnet, or earth, whatever it is. Earth, inside it, it is electromagnet only. North pole and south pole, if someone keep the magnetic compass, then compass would move only along north pole and south pole. Whereas compass is, I believe it's a minute magnet or something like that. So it needs magnetic field to rotate. In that fashion, Earth also behaves like a magnetic field or electromagnetic field only from the inside, whatever it is. Now there is an energy source. From energy source, there is a force vector, and because of this energy source, one item is moving from point A to point alpha. How much energy source is losing? That is capital F vector dot d of position vector. Force vector dot d of position vector. What is position vector? If I consider this line and this is origin, from origin I take any point on the line that is x comma y. I take any point on the line as x comma y, and then from origin, if I connect this, then this line is xi plus yj. This is position vector. If I differentiate this position vector, then it will bring another vector. That vector is parallel to this line. That is displacement vector. Why don't you use displacement vector directly? Because Displacement vector may not be static. This line we are talking, it is a straight line right now. It can be a curve also. Okay, if it is a curve, then item the bolt is moving in a curve fashion. If that is true, then displacement vector at each point in the curve is different. That is algebraic vector. So force is algebraic vector, displacement is algebraic vector. In that sense, we use force vector dot d, that is the differential part in integral calculus, force vector dot d of the position vector. Force vector dot d of position vector. What is the energy calculation of a force vector when it is moving an item in a curve fashion? Okay, then it is force vector dot d, that is calculus d of position vector. What is position vector? If I take any point P here, if this is the origin, then position vector is xi plus yj, where y equal to square root of a square minus x square as per the circle. Then it is force vector dot d of xi plus square root of a square minus x square j. Okay, that will come as dxi minus x by square root of a square minus x square j. Okay, so dot with f. If force field I dissociate with the orthogonal components f1 and f2, then f equal to f1 where f1i plus f2j. Then it becomes f1 dx plus f2 minus x by square root of a square minus x square dx or f2 dy. This is the energy calculation. Now we entered into path independence. Path independence means if I take a point A, an item is moving completely in a loop, closed loop, not necessarily circle, closed loop, and come back to A, then how much energy source is losing? That is integration from point A to A, or point A to B and B to A, whatever it is. Point A to A force vector dot D of position vector. If this comes as 0, if it comes as 0, then it is not, if it comes as 0, it is not necessary that for every closed loop it will come as 0. For circle it may come as 0, but for a maze kind of thing or for a parabolic kind of thing or for an arbitrary line, it is not necessary it will be 0. But anyway, if it is 0, then it is candidate for the path independent. Path independent in the sense that the net energy calculation is dependent upon begin point and end point only, not on the path. This is what in a very detail we have talked about. Now, what are the way to talk about the path independent? Path independent means if this is earth, an item is falling like this from here to here, then earth is losing energy because earth is working. That's why it is moving. For free, nothing would move. If that is the case, then whatever earth is losing energy when item is moving from point A to alpha, if this item move in a circular fashion from A to alpha, on a zigzag manner from A to alpha, or in a parabolic manner from A to alpha, in a staircase manner A to alpha, doesn't matter. Earth loses same energy. It is path independent and dependent upon the Earth gravitational force and point A and point alpha only, or point A and point B only, not on the path. This is called path independent force field, path independent energy source. Okay, what are the way to prove it is path independent? If in a circular region, if in a circular, in a curve closed region, in a closed region, if the line integral or energy calculation of force into displacement vector or force vector dot displacement vector or force vector dot d of position vector, if this comes as 0, if this comes as 0, then it is candidate for path independent. Tell me the exact proof, not candidate of path. Okay, if you have f1 dx plus f2 dy is the net calculation for the energy and it comes as g, it becomes g f1 dx plus f2 dy. If it becomes an algebraic function called gxy, small gxy, if you do dg by dx and it becomes f1, if you do dg by dy and it becomes f2, then it is path independent in the sense that net energy calculation G is only dependent upon F1 and F2 force field, not on the direction. And then integration from A to B, then on limit. So begin point A and end point B, the net energy calculation is dependent upon, and force field it is dependent upon. So if I have need to calculate the energy calculation, then F for the force field capital F, that is F1 I vector plus F2 J vector, that is the vector. Then force field dot D of position vector, that is Xi plus Yj. F1 dx plus F2 dy, that is energy calculation. If the result comes as G, that is an algebraic function. dg by dx is F1, not necessary. But if it is dg by dx is F1 and dg by dy is F2, then certainly this is path independent because G is only dependent upon F1 and F2. Okay, if that is the case, that dg by dx equal to F1, dg by dy equal to F2. Now dg by dx, please differentiate once again by dy. dg by dx dy equal to df1 by dy. dg by dy equal to F2. dg by dy dx equal to df2 by dx. Now dg by dx dy or dg by dy dx is same because it is dg by dxy plane. Here it is dg by dxy plane or yx plane, same thing. In that sense, if it is path independent, then df1 by dy equal to df2 by dx or df1 by dy df2 by dx minus df1 by dy equal to 0. If someone proves this df2 by df2 by dx minus df1 by dy equal to 0, then it is path independent. Tell me the concrete way. The most concrete way to prove path independent is find one algebraic function g for which dg by dx is f1, dg by dy is f2. Then it is path independent. Guarantee. What about your other guarantee? That is df2 by dx minus df1 by dy equal to 0. That is another guarantee. Yes, this is the guarantee provided this, okay, provided. So in a closed loop, if I take the closed loop, in a closed loop, it should be, if I take a closed loop, if I create a closed loop, in closed loop, if there is a kind of, I believe I'm doing too much. Okay, consider both as a permanent case. df2 by dx minus df1 by dy equal to 0. Consider this is path independent. Analogous to dg by dx equal to f1, dg by dy equal to f2. It is path independent. Okay, now there is one Mr. Green coming into the picture from somewhere. Now Green is saying that if the line integral or energy calculation in any closed loop from point A to A, if it is 0 with some certain path, then it becomes a candidate of path independence. Or df2 by dx minus df1 by dy equal to 0, it is again a candidate of path independent or it is path independent. Looks like they have relationship. So Mr. Green is saying that if what about if it is, so Green is saying that df2 by df2 by dy minus, sorry, df2 by dx minus df1 by dy, df2 by dx minus df2 by dy, df2 by dx minus df1 by dy, if this will be 0 if it is path independent, equal to 0 if it is path independent, and then line integral in a closed loop from point A to point A, if it is path independent, certainly it will be 0. If it is 0, then it is candidate for path independent from a particular path, not required for other path also from A to A, it will be 0. Okay, but if it is 0, but if it is path independent, df2 by dx minus df1 by dy is 0, it is path independent. If it is path independent, certainly A to A f1 dx plus f2 dy is 0. Okay, in a closed loop, the energy calculation line integration is 0. Okay, Mr. Green is saying if it is not zero, then if it is not zero from point to A to point A, then certainly it is not path independent. In that case, you are calculating the energy for moving a bolt from this point to coming back to this point. How much energy it is sucking from the energy source in the context of force field. This must be zero if it is path independent. Path independent means begin point and end point only it matters. If both are same point, if something is dropping like this, and then if I bring it back to the same position, net energy lost by the earth or by the system is same. Here it losing energy, then here it is gaining energy. So net energy is zero in the sense consider this, it is a potential energy. If it is a potential energy, if I drop like this, here potential energy is less. Here potential energy is high, potential energy is less. Here it gains kinetic energy, potential energy converted to kinetic energy. Now, if I bring it back to this location, their potential energy is regained. Net energy change is zero. So, so for path independent, it is zero. Now, Mr. Green is saying that if that is the case, then df2 by dx minus df1 by dy integration integration along dx and dy integration along xy plane where the region on the xy plane for a closed loop when we walk anti-clockwise direction, then it is calculation of line integral. It looks like funny because we know that path independence with if I have f1 dx plus f2 dy is g algebraic function dg by dx equal to f1 dg by dy equal to f2 means net result g is dependent upon f1 and f2 only, not on the path. So this is path independent. Now I proceeded dg by dx dy is df1 by dy, dg by dy dx is f df2 by dx. Okay, since both are same, these are also same for the path independent. So df2 by dx minus df1 by dy equal to 0 for path independent. If it is not 0, then it is not path independent. Okay, since df2 by dx minus df1 by dy is not 0, it is not path independent. Mr. Green proceeded on this. Now he is saying you take df2 by dx in a closed loop. Now he is talking about closed loop only. Df2 by dx minus df1 by dy in a closed loop. If it is not 0, anyway it is not 0. df2 by dx minus df1 by dy is not 0 irrespective of closed loop or open loop from a limit or non-limit. That doesn't matter. If this is 0, means gone. This is path independent. If it is not 0, Mr. Green is saying, in case it is not 0, and you consider a closed loop. Closed loop means integration from point A to point A, df2 by dx minus df1 by dy. df2 by dx is algebra, df1 by dy is algebra, algebra minus algebra, algebra dx dy, dx dy in a closed loop. So if I make a close, I'm not talking about circle only. If I take a closed loop, certainly this is not a circle. This is not a circle. Okay, it is some ellipse kind of thing. If I take any closed loop and if I walk anti-clockwise direction, so that region, it makes a region, can you see? It is a xy plane. If I take xy plane, then it is a region. It is a two-dimensional region it is making. Okay, now he is saying df2 by dx minus df1 by dy. It is an algebraic equation of x and y. This is a function over x and y. We can transform into z or fxy dx dy. It is full plane fxy dy dx dy. This is nothing but calculating a volume of a 3D. I have Okay, so I have a 3D. Okay, I have a 3D. This is 3D. Okay, this is a region on XY plane. Up. This is a region on XY plane. Now this is a 3D. This is the 3D that is above XY plane. Now, if I want to calculate the volume of this 3D, volume of this 3D, volume of this 3D will be if the equation of the surface is fxy, fxy is z value at any x and y. So at any x and y, if this is x and y, then this is fxy. If this is x and y, this is fxy. If this is x and y, this is fxy. If I connect all the points, whatever we are taking with different x and y, it becomes a sphere like this. Okay, if that is the case, then fxy dx dy is indirectly, it is a calculation, indirectly, it is a calculation for the volume of a sphere. This is what Mr. Green is saying. If you calculate these df, if you calculate df2 by dx minus df1 by dy and it is not zero, then it is a function over fxy because it will come as an algebra. Consider force field is 2xy I plus xyj. Then df2 by dx is y and df1 by dy is 2x. Y minus 2x is a 3D equation. Then y minus 2x dx dy will give a kind of a volume of a surface created by 2 by 2x by y minus 2x. Whatever the volume of surface is generated by y minus 2x, dx and dy would give the volume for that. If you calculate the volume, what is the reason? If you calculate the volume, then if you see from the top, whatever reason you are seeing, that is the reason against we are calculating. That reason is a closed reason. That reason is a closed reason for which we are calculating the line integral. Mind blowing. It is mind blowing. Means the reason is actually we are trying to calculate. Actually, we are in a phase of calculating energy calculation. Energy calculation means consider this is a bolt and I pierced it inside this line. Now, this is a force field. This is a force field. There is one energy source kept here. Because of energy source, there is a force field. Because of this force field, now this item is moving in a circle, in a closed loop from here and it is coming back to here. If that is the case, then what is the energy lost by the energy source? That is integration from point A to A and then df2 by dx minus df1 by dy dx dy. Okay, point A to A, that is the energy calculation around line movement. Green is saying that you can calculate in other fashion only. Think about a reason inside it. I was telling like this. Green is saying, go anti-clockwise, not clockwise, anti-clockwise. This is what he is saying. Go anti-clockwise from point to point. Then it will form a region. This region, if you take as an integration limit, where x is from this to this and y is from this to this, that is in xy plane. And this is the surface that is formed by df2 by dx minus df1 by dy dx dy over the region that is created by the line in that region. Then that is the also energy calculation. One energy calculation is from point A to A, f1 dx plus f2 dy. Another calculation is get the region of the closed region and get the limit of x and y. That is the closed region. So that is the limit over which integration has to be calculated. Integrand is df2 by dx minus df1 by dy and differential is dx dy. Then you calculate the line integral again. You calculate the force into displacement or energy calculation along the line again, but through the surface area. But it opens a door toward Jacobian kind of calculation. You can go with the different coordinate system now. This is what how it is precious. Anyway, now we are in a move to prove this Green's theorem. How to prove Green's theorem? That the df1, what is the line integral if item is moving from here to here? If okay, that is from point A back to point A. That is the limit. f1 dx plus f2 dy. That is same as this reason, the integration, double integration means area integration. Integration over this limit is over this region. This region what we see, circular region, full disk, this 2D from x minus something to something, y from y. If it is circular, then x is, and it is radius, it is center, minus a to a, and y is minus a square root of a square minus x square to a square root of a square minus x square. If it is a circular region, otherwise whatever limit region comes, and then df2 by dx minus df1 by dy, that is the integrand dx dy. You get same thing what you calculate a to a f1 dx plus f2 dy. This is what Mr. Green is saying. As per Mr. Green, it not only makes the life easy as far as integration is concerned, because we can use Jacobian, other kind of Jacobian and other kind of coordinate systems, but but it opens door to extensibility in 3D area also. Very precious. How to prove this? f1 dx plus f2 dy from a to a is the region that is created by a to a 2D region, and then df2 by dx minus df1 by dy dx dy. Now consider one rectangular region. Okay, consider there is, this is not my proof. Means I did from my way, but it is obvious proof. Anyone can do. Consider there is a rectangular region. If it is a rectangular region, then it is a closed loop again. Consider there is a rectangular region, and this is a rectangular region. So this is base. These are the two height. On top of it, again there is a line. So it is a closed rectangular region. One line, two line, three line, and fourth line. So this is a rectangular region. If it is a rectangular region, it is a closed region. Let's go by Mr. Green. Walk anti-clockwise. Walk in a way that this full region, the rectangular region, will come left side from you. If it come left side from you, then let's calculate the integration from here to here. The line integration or energy calculation from here to here. Consider this point is x0, y0, and this top point is x1, y1. If that is the case, then this point is x1, y0, x0, y0, x1, y0. This point is x1, y1. This point is x0, y1, x0, y1, x1, y1. Okay, x1, y0, x0, y0. Now I have to calculate the integration, line integration along the full path. Here, this will be only f1, f2 will be missing because there is no j component along this line. Energy calculation is f1 dx plus f2 dy. Now f2 along this line is 0, only f1 dx. Now f1 dx from x0 to x1, x0 to x1, x0 to x1, f1 dx is the net energy calculation along this line. Consider the top line. This line and top line, they are parallel to each other. Then it is f1 dx from x1 to x0. One is x0 to x1, one is x1 to x0. That is minus x0 to x1, same thing. So x0 to x1, x0 to x1, or rather, someone would say you are not including y. Okay, I'm including y. x0, y0, x0, y0, x0, y0 to x1, y0, f1 dx, f1 dx. Okay, minus again x0, y1. One is x0, y0, x0, y0 to x1, y0. Another is okay, x0, y0 to x1 y0, x0 y0 to x1 y0. Another is minus, another is x0 y1, x0 y1 to x1 y1. Okay, now the energy calculation for this line is x0 y0 to x1 y0 f1 dx plus this point to this point f1 dx, or minus this point to this point f1 dx, that is x0 y1 to x1 y1 f1 dx. Okay, now if someone sees it meticulously, then one is x0 y0, one is x0 y0 going towards x x0 y0 going toward x1 y0, x0 to x1, x0 to x1. This side also it is x0 to x1 only, x0 to x1. Here x0 to x1. This side also x0 to x1. Y is changing. This side it is y0 to y0, y0 to y0. And this side it is y1 to y1. Makes sense? Here on bottom x0 y0 to x1 y1, x1 y0, y0 to y0, y0 to y0. Here it is x0 y1 to x1 y1. Now the limit is x0 x1, x0 x1. But y here it is y0 y0, y1 y1. Now if I want calculation, if I have a function called y, g, function called g, I can write g as dg by dx into dx. Same thing. G, I have a function g I can write a dg by dx into dx, or differentiation of g and then integrating it with dx will come at g only. Similarly, if I have something called f1 dx and f1 dx integration from x0 and y0, x0 and x1. Consider this as a function x0 to x1 f1 dx. This is a function. Now if I differentiate this with dy and then I can integrate it with dy, same thing, right? Integration x0 to x1 f1 dx. If someone considers this as a black box, then d of this by dy, if I differentiate it with dy, I can just multiply it by dy. Same thing. Okay. If it is same thing, then whatever it comes, then I can set the limit. What I am trying to say is, if I have a function g, g of b, g of x, function g it has a variation in x, g and bracket x bracket close, small g bracket open x bracket close. This is a function g at point b minus g at point a, where x is b and x is a, gb minus ga. What it is? It is same as integration from a to b, dg by dx into dx, differentiation of g and then integrating with x, a to b. You will say, why it is funny? It is funny. Dg by dx, that is differential of g. If I integrate with dx, it becomes g. Then a to b, dgb minus ga, same thing. Similarly, I have integration, that is x0 y0 to x1 y0 f1 dx minus x0 y1 to x1 y1 f1 dx. Okay, if that is the case, then I can write it as integration from x0 to x1 f1 dx full by dx by dy into dy, because I have another limit that is popping up is y0 to y1. First integration has y0 full, second integration has y1 full. That's why it is prompting me to go for the example what we gave, that dg by dx into dx. Similarly, here whatever is there, x is x0 to x1 f1 dx dx d and in full big bracket, right? x1 to x0 to x1 f1 dx bracket close y dy into dy. Okay, and limit y0 to y1, same thing. You can differentiate anything with dy and then multiply it by dy, it will come as same thing, but you are respecting the y limit, that is y0 to y1. If that is the case, then it becomes a dual limit y0 to y1, x is x0 to x1 df1 by dy dx dy. Okay, so energy calculation for in a closed rectangle, when there is a rectangle that we are moving from this point to this point, this point to this point, this point to this point, this point to this. So for the line integral energy calculation, that is f1 dx plus f2 dy, in this component and this component only f1 will work, and that comes as y0 to y1, x0 to x1, that is the limit df1 by dy dx dy. Will it make sense? Okay, so now we got the energy calculation for this path and this path. Now someone can try this path and this path. So first he will go from here to here and then from here to here. Now in this calculation only f2 will come, f1 is not there, I component is not there. Then f2 dy is the integration, f2 dy from a point that is x1 y0 to x1 y1. Similarly, in this side, it will come as integration of f2 from x0 y1 to x0 y0, or minus x0 y0 to x1 x0 y1. So this integration will come as f2, integration of f2 dy from a point that is x1 y0 to point x1 y1 minus x0 y0 to x0 y1. Now both where y0 y1 is there, y0 y1 is there, y0 y1 f2 dy. Okay, and x is in first go x is always x1, and second go x is always x0. Okay, x1 x0. So integration is first integration is from x1 y0 to x1 y1. So x1 is there, y is y0 to y1 f1 dy, minus other side it is x0 y0 to x0 y1, again y0 to y1, same thing. Here it is x1, here it is x2. Here it is x1, here it is x0. Now the what we did last time, if I use same fundamental, x1 and x0, then it will become x1 minus x0. It will become x0 and x1. Limit is x0 and x1. Y is y0 and y1. x0 and x1. Y is y0 to y1. df2 by dx dy dx. That is the limit. First go we had calculated, I believe I did little bit different. So first what we calculated was x0 to x1, x0 to x1. Okay, x this this minus this minus this. Okay, that is x0 to x1, x0 to x1, and y is for this calculation, y is y0 to y1, y0 to y1, x0 to x1, and y0 to y1. Okay, I will confuse a little bit. But the scenario is that one is df2 by dx dy dx df2 by for this line and this line. This line and this line, the net energy calculation is df2 by dx dy dx. Integration limit is x0 to x1, y is y0 to y1. Another, for this line and this line, it is x0 to x1, y is y0 to y1, df1 by dy dx dy. Okay, one of the limit what we are saying in the other side is reverse. If I reverse it again to get what we are saying, it will become negative. That's it. So if it becomes negative, then net energy calculation is x0 to x1, y0 to y1, x0 to x1, y0 to y1, and then df2 by dx minus df1 by dy dx dy. If I add full component, this component we settled with x0 to x1, y0 to y1. Actually, it is other way, x0 to x1 and y1 to y0, something like that. x0 to x1, y1 to y0, df1 by dy dx dy, and this component x0 to x1, y0 to y1, df2 by dx dy dx. If I add 2, then one limit I have taken y1 to y0, I have to switch it. For that, it will become negative. In that sense, x0 to x1, y0 to y1, df2 by dx minus df1 by dy dx dy. That is the net energy calculation as far as surface area is concerned. Now limit is x0 to x1 and y0 to y1, then it becomes a area of this rectangle. Area, this area region of this rectangle, x0 to x1, y0 to y1, df2 by dx minus df1 by dy. This is a kind of algebraic equation that comes as a equation of a surface, dx dy. We will see more example into it. This is the Green's theorem proof that line integral or energy calculation along a line that forms a closed loop can be calculated with when we know the region that is making a two-dimensional region inside it. Integration over that 2D region with df2 by dx minus df1 by dy over xy plane. I won't say dx dy, xy plane. If it is xy plane, it can be modified into another coordinate system. Like example we gave, consider f is 2xyi plus xyj. Then df2 by dx is y. df1 by dy is 2x, y minus 2x dx dy, and limit is minus a to a, circular region. I'm talking about circular region, minus a to a, and y is minus square root of a square minus x square to y square root of a square minus x square, because for a circular region limit x square plus y square equal to a square. It is not linear, it should be rectangular. The reason we are saying it should be rectangular, then x and y will be independent to each other. Now x is minus a to a. If it is a circle, if it is a circular region under which we are calculating the line integral in a closed loop, the circular region has x is minus a to a when it is centered at the origin, x is minus a to a, and y is minus square root of a square minus x square to square root of a square minus x square, y minus 2x, y minus 2x dx dy. If I change it to polar coordinate system, dx dy will become r d theta dr, and y will become r sine theta minus 2r cos theta. Okay, 2r cos theta. Then r I can take outside, r into sine theta minus 2 cos theta. R and there r square integration is r to the power 3 by 3. Limit is 0 to a as per the polar coordinate system. A square, a to the power 3 by 3. I can keep it outside. A to the power 3 by 3. Sine theta minus 2 cos theta. Sine theta integration is minus cos theta. Minus 2 cos theta integration is minus 2 sin theta. So minus cos theta minus 2 sin theta. Now limit of that angle is 0 to 2 pi. 0 to 2 pi. So 2 pi minus cos theta 2 pi is minus 1. Minus sine minus, I believe it comes as, I'm sorry, it came as r, y is r sine, y is r sine theta minus cos theta minus 2 sine theta. Okay, then pi 2 pi 0 to 2 pi is the angle. So it will become 2 pi means minus 1 and sine theta is gone. For 0 also sine theta is gone. Minus 1 minus 1 and then minus 0 is again minus 1. So minus 1 and minus of minus 1 minus and then 1 minus 1 minus 1. Okay, I believe so. Minus 1 minus 1. I don't know. One sec. So, sorry. So, sine theta is minus cos theta. Other sine theta, I'm just leaving it because 0 or 2 pi it is 0, 1. Minus cos theta. Minus cos theta. Minus, let's keep outside. Minus a s power 3 by 3. Cos theta. Cos theta 0 to 2 pi. 2 pi, then it is cos 2 pi is 1 minus cos 0 is 1. 0. There is no work done. Looks like it is something that anyway someone can calculate. This is the way someone can calculate the work done. Someone can try with the linear calculation also. That is y, that is x dx plus y dy. X dx plus y dy. Okay, I'm sorry. That is f1 dx plus f2 dy. F1 is 2xy. 2xy dx plus xy dy. This is the calculation. 2xy dx plus xy dy, where y equal to square root of a square minus x square. Now it becomes 2xy, 2 into x into square root of a square minus x square dx. Okay, plus y dy plus the yth component, y f2 component, that is xy, that is xy. So x into y is square root of a square minus x square dy, that is minus xy square root of a square minus x square dx. X square root gone, x into minus x square dx. Minus, so here it becomes x into a square root of a square minus x square. 2 into x into a square root of a square minus x square dx minus x square dx. Someone can calculate and verify it is correct or not. Okay, so we will proceed on the Green's theorem. Probably this example I'll take it again, and then we will see what else we can fetch from the Green's theorem. Mind blowing, transforming the line integral into surface integral or volume calculation. Anyway, please do support us. +91 is the India country code. 9483160610 is the telephone number. 9483160610 is the telephone number. +91 is the India country code. We'll proceed on the vector and commercial calculus as far as Green's theorem is